Good morning. Hope you're all this morning. The sound working? All right, so let's make a start. So this week we're carrying on with the material we've seen last week. Last 2 weeks or so we've been looking at binary things. So we've looked at essentially simple logistic regression models where we've got Bernoulli outcomes, we've got single observations in individuals, and then we went on last week to look at binomial observations. So we've got several binomial trials. Now there was something like a binomial trial with some n and hopefully the same, well, maybe some p as well. There's several of those trials, maybe the same p is the idea, and we were looking at how they work. And this week we're moving on now to count data. So we're looking now here at the number of successes or the number of occurrences, sorry, not successes, occurrences of a particular phenomena, whatever that phenomena might be. And I'll give some examples later on of how these things actually work in practice as well. We'll discuss some things. Before I carry on, it seems to me that many students in this class are trying to simply pass by looking at tests and whatever else and doing very little other work. There's two ways of doing this kind of stuff. You can just simply pass by doing it that way. You can pass and maybe get a fairly good mark as well. There's cross-testing, looking at the test questions and the lecture notes and the labs, and that's all. Or you can do all the work and actually understand the stuff. You see, out there in the world, when you go there, you can't keep looking at things and guessing your way through that. You must know what's going on, because otherwise you'll have disasters. And well, luckily so far we haven't had too many of those in the world, but I'm pretty sure the way education is going at the moment, we're going to get some more of those. We could start off with, you well know that the education system isn't very good in Australia, at least anymore, than it used to be about 20, 30 years ago. Compare that with our near neighbors, even Singapore, for example, India, China. They're killing us, man. They're killing us. They actually value education, they spend on education. To get into a good institute in India, you've got 1.7 billion people altogether. You have over here in Western Australia something about 4,000 or 5,000 year 12 students trying to get into universities. There, and so quite a few of them get it actually in that sense. There, for every seat there is something like a few thousand students, and it's really tough to get in there. You can't just walk into the institute like that, like they do over here in Australia. You have to go through interviews in the best institutes. Don't make it so easily. And then, here we have to be nice to you. Not that we're not nice anyway. Some of us are nice, full stop. But there they kill you as a student. None of these things about student experience. You can even ask him. Student experience to them means we're going to drag you through absolute coals to make sure you come out the other way shining at the end. You actually learn something. You become something that's worthwhile. That's, to me, is a graduate, right? None of this trying to parse things by looking at assignments, questions, and solutions, those kind of things, working through there, essentially just hobbling your way through a degree. That's one way of doing it. You might actually make a living as well. But is that the purpose we're all about here? To me, that's just a waste in many ways. Learn the stuff, study it properly. Anything you do, what's the point of doing that thing unless you do it well, yeah? Extend yourself, stretch yourself. There are some students who do that and do it very well. But there are only very, very few number of those. Very, very few indeed these days. I complain about this a lot. Back in my days, even before my days, I've been here since the 70s. Thank you doesn't show. Thank you. I know. But in the 70s, to get a first-class honors in maths and stats, 1 or 2 students a year would get it. And it was really good. There were years when there were no first-class honors in computer science. There weren't any at all. The top student was a second up or 2A honors degree. These days, last year in our department, every honors student we had got first class. That to me indicates a level. You go to India and other places in the world, I keep saying India because they're really coming up. So same in China, you look at Singapore, for example. To get into the top, so in the class, there's 2A degrees will be something like our first class at least, not better. So for goodness sake, please pull your socks up. In Australia, I keep saying, we have very little issues in the way of problems. It's stable, whatever the thing is, maybe bad or good government, but at least it's stable, yeah? We don't have wars and bombs going around, flying around all over the place. You can actually work in an office and get something done without bribing somebody. You know, things are very nice in Australia in many ways. So for goodness sake, take advantage of it. What stops you guys flying? I'm not talking to you in particular, but just generally speaking. What stops you flying? You know, take off in the world. Show the world what you're worth. If you don't, you're going to be left wanting. You know, we can boast about this and be all smug like some people in the world and some of our politicians are. But boy, you will see in the next 10, 20 years how far behind the world we really are. And then you're going to be playing catch-up. And playing catch-up is hard. Unfortunately, the human nature is such that unless things go really bad, we don't change ourselves. You know, we had this absolutely wonderful chance. Come COVID, you know, they talk about the short circuit, the circuit breaker lockdown things to try and get rid of COVID or whatever, suppressor thing. Well, we also had a short circuit breaker last year with the lockdowns around the world where the environment suddenly got cleaner. We learned to live differently a little bit. And there was a great chance to change the way we think and live so we can be all friendly towards the environment, rethink our economy. It all went to waste. Nothing changed. Back to the same square. Until the next disaster. How long before we wake up to the fact that it's not all very good out there and we could change some things about how we live, how we do things? How long will it take? What will it take? When will the thinking change to just making money from everything and only valuing money? You know, I'm surprised that people these days, especially young people, all of you, including your parents and those who have kids and who will go to university in 5 or 10 years' time, why don't you demand that the government actually funds education properly? Because to me, universities are the powerhouse of the economy. You don't have universities, you've got no economy just about. And the government says we can't afford free education or free health and all the rest of it. That's a very easy thing to say because then if you say no, you've got to do nothing more, right? The government's job is to work out how you can afford free education, how you can afford free health care. That's their job. And to me, the solution seems simple. You see, the way the modern economy goes is it enriches individuals and impoverishes nations. We had free education in the 70s. You think that Australia was richer then than now? We have got more money in the world and more money in Australia than before. So why can't we still have free education and free health? Well, because the governments are cowards. Absolute cowards. You know, they just can't seem to take on the big corporations to make them pay a fair tax. Why not? Amazon says we live in Australia, bye-bye. See you later, mate. Because something else will come up from Australia maybe, who knows. You know, Google says we're not going to operate here, thank you, get out. We'll live without you. Where can they go? They're going to still work in the world, right? It takes one nation to stand up to them and the whole world will stand against them. But no one is willing to do that because everybody is just interested in making sure they keep their seat in parliament. For goodness sake, do something good for the country and you'll stay there anyway. Anyway, that's enough of my speech about all this stuff. Maybe you can see my frustrations and how the world's working at the moment. So back to this stuff here. So I please advise you, don't just go through and pass this stuff. Actually understand the thing. You know, actually it is very interesting stuff. I make my life out of this. And when you go out there, you realize how important this really is. You can't become a data analyst by knowing pockets of things. You must know a lot of it. New things come all the time. There are things, you know, you ask any member of staff in here, the maths and stats staff here, there are things we don't know. And we know things very well. We teach the stuff, right? But there are things, new things come to us all the time. We have to learn about them, find out about them, maybe make some new things as we go through here. So these kinds of Poisson models, you know, people ask me in the kinds of questions, I'm not complaining because I don't mind asking questions, but the kinds of questions I get asked sometimes by emails just shows that people haven't looked at this stuff. Obviously, I haven't looked at them. All they want is answers to get these tests out of my way and get a pass mark. To me, that's a waste of time. Anyway, Poisson regressions. So far, we've had binomial data, and now we're going to go further. So the kinds of models we've seen so far have been these log linear models for the binomial outcomes, or binary outcomes essentially. whether they're actually binomial observations, meaning I've got an observation on a binomial distribution NP, or whether they were simply just Bernoulli single observations, one per trial, as we saw in the test question. Either way, we can still use the same kind of models with slight differences in the way they're fitted. When we get to Gaussian, the normal stuff is no problems at all. Some of the assumptions there were constant variance. It doesn't hold in the case of binomial and all the rest of it, because the variance is a function of mean. And the data structure we saw earlier, this is all last week's stuff as before, except that now we've got the output, or the response is binary as opposed to what we had before. So this is here the Gaussian and logistic regression stuff are slightly different in what's happening there because of the outcome being binary, not just oh, you can't see that. If you tell me earlier. Anyway, here we are. So binary stuff, yes, as I was saying earlier, we saw the logistic regression stuff where we have predictors which are linear, but whether it's a binary or Bernoulli distribution, in other words, just one observation per person, one per record, or whether we've got actually binary, meaning we've got observation on actual binomial distributions, as we saw last week, the same kind of model works. With Gaussian, the assumption was we had a constant variance thing, but we know that with the binary distributions, the binomial, the mean and the variance are linked. Variance is a function of mean. So we now look at something slightly different. Here's the case in studying that we look at briefly here. This is from an 89 paper about elephants and mating. These kind of things are important because when you have rare or extinct animals or the endangered species, it's important to make sure that they can have enough of a pool to sustain themselves, because usually when the population falls below a certain critical threshold level, the whole population dies, unfortunately. So here, this is looking at the number of matings they have in, this is I think over 8 years or so. And so you can look at the data, you can look at the paper as well. So this was a study of 41 African male elephants over 8 years in Kenya. And the age of the elephant and the number of successful matings they had over this 8-year period is what's looked at here. Now the question here is, we can't use actually a logistic regression model here anymore, because the thing is, data is not binary. It's not just 1 zeros anymore, or it's not in any sense binomial either, because it's not binary and not binomial. So neither of the previous models we saw will be able to work here. Because if you think of it's binary and binomial, especially binomial here, how many trials do we have? Do we have a fixed number of trials, or do we have a single trial? And do we have a probability of success? We don't have any of those. What we have is count. Of the number of occurrences of some phenomena, whatever the phenomena is. Now, those who might have done some probability theory somewhere else will realize what we're looking at now is what's called Poisson distribution. And so here things are a bit different. Unfortunately, you'll find out in the world, if you look around, people take this kind of data, we've got actual counts, and model them as just normal regression. It doesn't work that way at all. It's not going to work for many reasons, as we'll see later on. To start off with, it's not continuous data, it's count data. So here, the point is, here's the data, the elephant, the age of the elephant, and the number of matings they've had. So it's a pure count, nothing about I've got 10 trials or whatever, it's pure count here. So we're looking at the number of matings as such. And this is what Poisson distribution is all about here. Now, if you could look at the data here, you've got age, which is, you can think of as continuous. Yeah, it's from 27 till 52. But the matings here go up till 9 only. Now, it does look as if the matings is right skewed, because look at it, we've got this first quartile is at 1. and then we've got the mean of 2, and the third quartile is at 3, but the maximum is 9. So it looks like the data looks like this. A lot of it is here. Up till about 3, you've got 75% of the data. A lot of it is there, but then it tails off rather long here. So it's right skewed. Now I've drawn the thing as continuous. Of course, all this discrete, just to give us an idea of what it looks like. So it's right skewed. There's one little problem there. So it certainly isn't normal. So you look at the histogram, there it is, very much so right skewed, very clearly right skewed, a bit of a bump there, and then it tails off over here as we go through here. So people might think this 9 is an outlier, this is a normal distribution, you might think it's outlier. It's not normal at all in this case, and people will try and make it normal by logging or whatever else. Maybe to some sense that might work, but the idea is you can do far better than that. So what we're looking for here is, with the data are counts, similar to binomial, but not the same as binomial, because binomial has a fixed number of trials and we count in the number of successes. Here we just have counts, how many of these things occurred. And this is different in many senses. As I was saying, there is no probability of success as such. And of course, binomial has an upper limit that's fixed. Number of trials is given to you. Whereas the elephant number of matings is not fixed. It could be any number at all. Of course, it won't be as large as, say, 5 to the 7, 8 years. There won't be like that at all here. But there are many phenomena that look like that. So, for example, if you take a look at the number of looking at, say, a number of I'll just call them moles for the moment, on the skin of a person, trying to diagnose for cancer, whatever else, number of galaxies in some part of the universe. Whenever you're counting something and you're looking at things in some fixed, generally speaking, we say volume because it's a genetic term. It could be just area for that matter. It could be actually along. Most ecologists do things like looking at a transect. So they'll take a look at a piece of area they're looking at and draw a transect that way and look at every sort of 5 meters to see how many of things occur there. So those kinds of things, we're actually counting things in some volume. It's a generic term, but it could be, as I say, just a straight line or some area, whatever else we're looking at. Counting of these kinds of things are modeled as a Poisson distribution. And the thing with the Poisson distribution is its parameter is a mean. This is the mean number of occurrences. And because it's counting, it takes all non-negative integer values. So 0, 1, 2, 3, 4, as high as you like. Of course, as you see, often it just tails off very, very fast as well. But generally speaking, as a Poisson count, it can keep going forever. Lambda is the average number of occurrences, or average rate sometimes it's called here. And the reason it's called rate is because the average here is fixed, looking at whatever you're looking at. So if I'm looking at, say, an area of land, then that area or that unit area may be my unit. So in that case, it'll be the average rate is rate per that particular area or the volume or whatever I'm looking at here. And of course, lambda has to be positive if it's a count. Probability mass function here is simple. It's e to the negative lambda, lambda to the y and over y factorial here. So it's a particular form here where y takes the value of 0, 1 all the way to infinity in practice. The Poisson is one of those distributions, the only one, where the mean and the variance are equal. Of course, with binomial, you saw the mean and variance weren't equal. In fact, the variance depends on the mean as well. Both depend on the parameter p and on the parameter n as well. So here, the variance and the mean are the same, and this is one measure of Poisson. If you're looking at an account data and you want to look to see whether it's Poisson or not, an appropriate Poisson model, you should look at the mean and variance and see if they're close enough. And this is something we'll look at later on, because in some of the data we'll see, which are essentially count data, you'll find the variance is too small compared to the mean, or too large compared to the mean. And they're both a problem, because if the variance differs quite a lot from the mean, then the Poisson model doesn't hold anymore. And if you try and fit the Poisson distribution, you'll find all kinds of things will go wrong. At least if you aren't careful, you might just believe the results and they will not be right, or at least not the best. So the things I was saying earlier here is the examples of Poisson is things like the number of earthquakes per year. So my lambda here will be the average per year. So lambda here, if I say is a Poisson lambda distribution, lambda equals mean number per year, number of earthquakes per year. So this is my rate in this case. And the way it works is, if I suddenly start looking at 2-year intervals, my mean simply doubles. I've doubled my volume here from 1 year to 2 years. And if I'm looking at the number of earthquakes in 2-year intervals, then the mean suddenly will also double in the same way. It scales in the same way. Number of car accidents at an intersection per day. So it's per day. That's where it's a rate. So mean here is the number of accidents per day. Number of typographical errors on the page, sharp corrects per year, those kinds of things. As long as you're counting something in this sense, you will find they're all over some fixed interval, time and space, whatever it is, either fixed time interval or fixed space interval, whether it's area, whether it's volume, those kinds of things we're looking at here. And the average is a rate, essentially, is the number per whatever that interval happens to be here. So that's Poisson in this sense. Now, this was some history of this stuff here. So there's Simon Poisson, who started all this thing, this French mathematician, and published his paper here. So his idea was that when in the binomial distribution, when n becomes very large and the probability becomes very small, you approximate a Poisson distribution this way. So the binomial becomes approximately Poisson. And the problem was that if you had a large n and small pi, calculations could become difficult for binomial distributions. So we approximated that by Poisson to make calculations easier. Poisson's easy. You've got a formula, you can use the formula very easily here. But for binomial, it becomes more tricky and more difficult here. And of course, we've also seen the normal approximation to binomial distribution. You can also approximate Poisson binomial. Those kinds of things also happen in probability theory, but that's not of particular interest to us. But the Poisson distribution is very important for many reasons, as we saw. In fact, one of the early applications was the number of deaths by a horse or mule kicks in the Prussian army back in the 1800s or so. So there was one model that was used very early here. So the Poisson distribution here, this is just the R code for trying to look at what happens when we take a look at this here. So the R command is essentially Pois, P-O-I-S, but whether you have D there for distribution, which means it gives you the actual probability for a single observation. If you have P, it gives you the cumulative probability of being less than equal to. And of course, you've got R, it gives you a random observation or random simulation from the Poisson distribution of the appropriate parameters we have here. So if I want D Poisson, then I want the value here, which is the number of successes I want here, and I want the mean here as well. So you need to give both of those things to that distribution here. So here are some plots for that, and it won't take you long to guess what's going on here. You'll find this is for 1, 2, 3, 4, 5. So this is going to be for 1 and 2, and I suppose it says 5, but I can only see 4 there. 1, 2, 3, 4. Is there 5 or 4? 1, 2, 3, 4. I can see only 4 here. So it's not very hard to actually work out. 1, 2, 3, 5. That's what's going on. It's not a 4. There's no 4 there. It's easy to see what's going on here because you see the mean is meant to be the value of lambda here. So this is the smallest mean. This is the next. The mean here is 2. So you can see the hump or the highest probability occurs around 2 here. For this is around 3 here, and this is around 5 over here. But you can see here, by the time you get to lambda equals 5 here, this looks like normal. And so if you're looking at this kind of stuff here, if you're trying to approximate the Poisson distribution by normal distribution, well, then you'll use the mean from the Poisson distribution. So it'll be normal with mean lambda and variance also lambda in that case. And we'll see some of that later on here. And we might relate this back to something else we've done earlier somewhere else. So this is what the distributions look like here. As you go further out with the mean, it becomes more and more symmetric. But if you go too far out, what you'll find is it becomes a bit left skewed as well, because as you pull the tail this way out here, this becomes a bit more skewed to the left. You still have probabilities for 0, 1, 2, 3, 4, although they'll be very small, but you can find very easily it'll actually skew the other way here. So in this case, the data we've got is the counts of successful matings, which is while I equals 0, 1, 2, and so on, whatever the data says here. And lambda here is the average rate or the mean number of successful matings. So we're going to model our data yi as Poisson lambda here. So we're trying to estimate here lambda. We're trying to work out what lambda is. But of course, the lambda won't be the same for each elephant. It may be different for each elephant. So we'll see whether we can actually model something here depending on the age of the elephant and other covariates here. So I want to write n as the data here for the n elephants, and n estimator for the average number of matings is simply the average of the data. So average all the number of matings we've got here. Average of the data will be fine. And the sampling distribution of lambda head, the sample mean here, is we know it's going to be normal approximately with the same mean as the mean we get from here, and the same variance as we get here. So the variance here is mean here is mu is equal to lambda, and the variance of the Poisson is lambda. So variance with sigma squared is lambda. This is sigma squared upon n, if you like. So the usual stuff we had was it was approximately normal with mean mu and variance sigma squared upon n. Well, here for the Poisson, the mean actually is equal to lambda. So Poisson lambda has mean as lambda, and the variance sigma squared is also equal to lambda. Put those things in the particular normal distribution, you get exactly that here. And so for large sample size by central limit theorem, this sample mean is approximately normally distributed. It doesn't really matter because we're not going to use it very often here, at least in this context. We can still use it at least to work out things like confidence intervals. Other than that, there's not much use here. We can use the Poisson directly. So here it is straight away. Confidence interval in this case will be approximately given by this lambda hat observed, the data sample mean from the data here, and then 1.96 times the standard error of the lambda hat here. And the standard error here simply was lambda upon n square root of. So now it becomes lambda observed over n square root of. Be careful, this is the root of the both things here, lambda observed as well as n over here, because our sigma squared was lambda. So sigma is the square root. So this is just a formula straight away for the confidence interval, easy to use, and you can work it out by hand or you can use R, whichever way. So here's the calculations for the data from the elephant mating. We've got here lambda hat is simply 2.68 or so, the sample average, and the standard error is going to be lambda hat on n square root of. That's been calculated here. And here is the confidence interval for the mean number of matings in the 8 years, about 2 to 3 or so. And so the same kind of interpretation holds here. So if you have repeated observations on the same sample size, 41 elephants over 8-year periods, you'll find that 95% of the confidence intervals will contain the actual true mean number of matings. So we know that how that works here. Nothing different from that. So if you take a look at things like hypothesis tests for Poisson distribution, then null hypothesis, for example, if you want to test things like is lambda equal to 2 or not. So null hypothesis is lambda equals 2 versus lambda bigger than 2 here. So we're looking to say whether it's equal to 2 or bigger than 2 here. The sampling distribution is approximately normal here. I don't need that, by the way. I can use the Poisson directly here. So here I'm looking at the hypothesis test this way. Lambda hat is bigger than lambda observed. Our lambda observed here from the data we got was 2.1 something. You'll go back a second and you'll find it here. we had the thing is 2.6 actually. 2.6 is the lambda observed. So we're trying to see here whether the probability of being bigger than lambda observed given lambda is equal to 2 here. So the normal distribution I'm going to use is with lambda over here. It will be normal 2 over n, as you can see. I use the null hypothesis value all the time in hypothesis tests, because that's the value I assume to be true, and I'm trying to work out the probability, if you like, of observed data given that my null hypothesis is true. In this case, the p-value is quite small, so we can reject the null hypothesis and we'll be okay. The other way of doing this particular test, by the way, a more accurate way of doing this is going to be, I've got my observed data here is the number of successful mating, which is Poisson lambda, and my observed value here now that's a bit tricky because I don't have a single observation. I've got several observations that will be a bit more tricky, so I'll ignore that. I really need something better than just that. It requires a bit more mathematical background, so that's fine. You can do it that way as well, Poisson distribution. In fact, one of my favorite questions was hitting this kind of question in the exam somewhere in first year when I taught that stuff. But yes, you can use the Poisson distribution exactly. However, this is just a single point hypothesis, and of course this is just average for all the elephants. And as you can see here, we reject the null hypothesis. We conclude that the average number of matings per 8 years is actually more than 2. But our interest is actually to do some modeling. We'll see here. So here's the data, and this is the Poisson distribution with the particular mean superimposed on that. So you can see what I've got is the usual step. I've actually got the histogram plotted first, then I've got my grid here, the sequence of points from 0 to 10 in lots of 1, and I've got the points plotted over here with the probability as well from the Poisson distribution, where the mean is used as what I've got from the data. Lambda hat was used over here. So you can see that the actual model here with the lambda hat I've got actually follows it fairly well, fairly well indeed. The only problem is this 9 over here. It seems to be too high. So there's one problem we have to be careful of, because we expect the Poisson to die away and not suddenly have another bump somewhere else. If it does have another bump somewhere else, there are issues there, and we can consider what to do with those as we go through. Any questions so far? All right, so some modeling stuff. As usual, what we're modeling here is going to be the expected value of y here, which is lambda. But the lambda here is some function of age. That's the only other variable we have here. So the mean of yi is lambda I, which is equal to some function of age. Now the problem is that in the Gaussian or the normal regression, we'll actually be modeling the mean. But we don't do it over here. As we saw with binomial, the problem was there were several problems. One was that the mean and the variance were not independent, if you like. The mean and the variance depend on each other. As the mean goes up, so does the variance. The same thing happens here with the Poisson distribution. And the other thing is, it's not actually continuous. Observation actually account here. And so the usual problem as we had with the binomial was that if I actually try to model the actual probability of success, because it was regression, the probability could, because of the regression equation, become negative below 0 or also above 1. Likewise here in the Poisson, the mean is bigger than 0, but regression may go negative as well. So to avoid that, we can't use simply just the normal regression stuff. What we do is we actually look at the log of lambda. And I was saying to you earlier that we've got essentially Poisson distribution is skewed, and the log does pull the tail in. Yeah, log tends to make things more symmetric by pulling the tail in. High values become smaller, and the small ones don't change very much. So log is what we actually model here. So log of lambda is the regression equation. So in other words, the expected value of yi given the data here, the other coordinates, which log is what we look at. So log of lambda is the usual regression. This is a lot simpler than binary regression in many ways, because I don't have log odds here. I just have log of the mean here, which is much nicer in many ways. And so the mean simply transforms an exponential over here. There are similar problems to how to interpret this as we saw with the binomial regression. We'll see this afterwards. So there are issues here, but essentially to find the mean again, you just have to take exponential of the particular equation, and you've got the mean straight away from there. So nothing too different here. Probability of yi is this Poisson distribution probabilities here, and we've got the result from the regression equation to go backwards. The mean and the variance, as we saw, are related. As the mean increases, so does the variance, and the other way around here. So they both depend on the same parameter. The Poisson regression here, as we like to represent the thing this way, is as the mean goes up, then what we see over here is the distribution. If it was normal regression, you'd find the distribution to be symmetric and normal around each of those particular mean points, and will have the same spread, which means it indicates the same variance. Here, as the mean goes up, the variance also goes up, and the whole thing moves up just a little bit as we go through here. And the log here, of course, means the whole thing is nonlinear here. So Poisson regression here, the way to interpret the coefficients is, if, as we saw before, if I have this regression equation here for lambda a written in terms of the exponential, is e to the beta naught and all the rest of it, so it becomes a product of the exponentials of the individual terms here. So a unit increase in, say, x1 here, I increased x1 by 1. It was a before, now it's a plus 1. Everything else is the same. You can see what happens over here. So everything else being the same here, all I have is this extra term of e to the beta 1 that comes from this term here is e to the beta 1a times e to the beta 1 times the 1. And so it's the same as I had before, except I've got an extra term here of e to the beta 1. So if I increase one of the coefficients by 1, then the mean will increase by, or it will change by a factor of e to the beta. If beta is positive, then e to the beta is bigger than 1, so the whole thing becomes bigger. If beta 1 is negative, then e to the beta 1 is going to be less than 1, so the whole thing decreases. In other words, negative effect or positive effect. So this is the case with a unit increase. Of course, if I increase the thing by 2, if I make it a plus 2, you can see I'm going to get a 2 beta 1 here. So it's beta 1, 2 beta 1 here. So it becomes 2 beta 1. So in other words, the effect is actually now e to the beta 1 squared. So increasing by 2 means that the mean will now change by beta 1 squared, and so on and so forth for 3. Usually, we have continuous variables. We can think of this increase of 1 or 2, or categorical variables where you go into different levels, and each level in that case will have a different coefficient. So we don't have to worry about that in that case. But otherwise, in assuming that my x1 here is continuous, as I change x1 by 1, then the mean will change by a factor now of e to the beta 1, e to the coefficient I'm looking at. So be careful with that kind of idea. It's tricky sometimes if you're not careful. If I change by 1, it's just the factor e to the beta. This 2 is going to be e to the beta squared. So be careful with that. As we said earlier here, if beta 1 is positive, then it's an increase. If it's negative, it's going to be a decrease. If it's 0, of course, there's no change at all. So here is an example of the actual calculations. If beta 1 is 0.5, then e to the beta 1, this thing about e to the beta 1, the change, is going to be 1.05, which means there's an increase of 5%. So I can say that if I increase this variable by 1, then the mean will increase by 5%, everything else remaining the same. If it's negative 0.05, then you can see it's the opposite. It's e to the negative 0.05, this 0.95 or so, approximately a decrease of 5% in this case. So in this case, I can say the mean will change by a factor of 0.95, or it'll decrease by 5%. So be careful, I can say that very easily. And this is usually the easiest way to interpret this kind of thing. If I change this particular variable by 1, then the mean will increase by 5% or decrease by 5% if it's negative. And that's the simplest way to write these kinds of things down. The parameters here can be estimated in many ways, least squares or multiple or maximum likelihood or whatever else. So all these methods work here, and so R will do all the hard work for us. The command here as before is glm, but the only thing is now we don't have a binomial or link here in this case anymore, so the family will change. And so what we need to do here is I've got to specify the family as Poisson. And now the Loglink is the default. This is the default, so that can be omitted. You can omit the actual specification of the link function. as you'll have seen me do quite often in the Poisson, in the binomial regression. For binomial, the Loglink is the default, and for Poisson, the Loglink is the default. So you can just simply do the modeling as I have over there. Elephant GLM1 is GLM matings by age here. That's the only variables I've got is the number of matings plus the age of the elephants. The data is elephants, which contains those variables. Their family is Poisson. As I was saying, I don't need the link function. That's the default anyway. And here's the output, nothing different from the usual regression output. Be careful, again, I'll point out this thing, dispersion parameter. We need to look at this afterwards to see what's going on with this and why it's important. The other thing that's important here is going to be, we saw this idea of the drop-in deviance. So the null deviance, where I actually have beta of the age is 0, is going to be 75 odd with 40 degrees of freedom. Whereas if I fit one variable there in the model, then the null deviance drops by quite a bit, almost 24 or so. The degrees of freedom is 39 over here as well. So this also will indicate to me in some way these two, excuse me, these two will actually look at together and try and relate them to each other later on to see what the problem is. All right, so here's the output, and you can see pretty easily here that the equation for my regression, I'm sure it's written somewhere later on here exactly. So in this case, my regression equation is going to be simply log of lambda I. There's a constant term here which is negative 1.58. And I've got then this 0.06869 times the age of the elephant, which if I turn around to write just for the lambda I, then I've got lambda I here is e to that power, so it's e to the negative 1.580 and so on. So while looking at this equation here, you might think, well, I've got a negative here, that may be a problem, because we know often in normal regression things, when the constant or the intercept term can be negative or something else, it mightn't make sense. Here it's fine because I'm taking it exponential. So here, because it's negative, the mean with e to the negative 1.5 is going to be less than 1, but the age here is quite large, you can see, so that actually will temper this down a little bit. For a 1-year increase in adult male elephant's age, the number of successful matings here will be changing by a factor of 1.07, so it will in this case will increase, which means a 7.1% increase in the average number of successful matings. So as the age grows up for these elephants, the number of successful matings actually increases by 7% per year. So it's 7% for the first year, and it's 7%, another 7% here essentially is squared now. It becomes 1.06, well, it's 1.07 squared, which is going to be increasing, as you can see, and so you have to be careful how this is looked at. So instead of usually looking at, say, a 1-year increase, because that's just a little bit tiny compared to the age of elephants, we might look at, say, a 10-year increase. As being more meaningful here. And so that will give me e to the 10 times this. Which actually becomes essentially my 1.0711 to the power 10. And so that will be a reasonable change in percentage terms if you look at it that way. So I can say for a 10-year increase in the age of an elephant, the number of successful matings will go by this many percent, whatever the percent is, by looking at what that number comes out to be. Any questions so far? Model fitting is not difficult in many ways. The problem's going to be arising when you actually make sure that the model assumptions are satisfied and also how you interpret them properly. As a prediction, for an elephant that's 27 years old, the number of successful matings over 8 years is 1.3 or so. Now, as before, as always, whenever you fit a model, in this case we've only got one variable, that's significant, but if you've got more than one variable, you'll reduce the model by taking off the non-significant variables one by one until you have a reduced model. And so that kind of reduction essentially is based on the p-values. That's the Walls test we've seen before. You can also look at drop-in deviance tests here, but the Walls is what's used quite often. Drop-in deviance isn't as good for models as in general. It looks at whole models, not just individuals. But you can drop one term at a time and take a look at the thing as a deviance test as well, as we did last week, I think. As far as the assumptions of the model are concerned, you also got things like the Poisson residuals, which to look at, and all those kinds of things, as we shall see later on here. So we need to also test for the model assumptions, and there are some assumptions we can test for, and some we'll have to look at later on. Hypothesis test is simple, beta 1 equals 0 versus beta 1 not equal to 0. The p-value here is quite small, so essentially that means that it's a significant result based on 5% significance level. 95% confidence interval we saw is going to be beta 1 observed plus or minus 1.96 times the standard error of beta 1. And the standard error of beta 1 here, I don't have to worry about or stress about, because of course it's given to me in the R output. If I go back a second here, you'll find here it gives you the standard error of each of the parameters. So here I've got the thing is 0.01375. So I'll simply use that for age. So for 95% confidence interval for beta 1 here, oops, too far. It's as we said, that's for beta 1, yeah. Which is here. But I'm often interested in not beta 1, but e to the beta 1, the actual mean change, or the mean corresponding to that. And so it's just a matter of taking a look at the exponential of that. That's fine. While you're in this kind of idea, so the model I fitted here was called GLM1, I think, just making sure I've got that correct. What do we call it? GLM1, elephant is GLM1, right? So something like this, you may be aware of this, will simply give you the coefficients. And so you can take its exponential quite easily. So exp of that, especially if a model is about sort of 10 or 5 or 10 or 20 variables, exp of that gives you all the exponentials straight away. You can work it out straight away from there, and you can work out confidence intervals for individuals if you need to do so here. And so as it says, if 1 year rise in age, we have a 95% confidence interval for the average change as being between 4% to about 10%. Same idea, this is just a frequentist interpretation of this. So it just essentially means that 95% of the intervals of that kind repeatedly will give us that. The average rate of success here, the data is given to me, the age and the matings, and all we've done here is plot here. If you see, the grid's been constructed over there. And then what we've got is, first of all, just the dots, which are actually the actual data observations. And the line here is what we get from the regression equation itself, just fitted on top of there with the mean, essentially. So this is the mean number of matings. And this, of course, is age over here. So that's okay, just seeing how the thing fits. It won't be straight line or linear. If you actually log the data first before plotting it, then you should be expecting to get a straight line, so you can try that yourself. Instead of plotting the data, I can plot the log of the data, and because it's now on a log scale, I can actually plot the straight line equation of the regression, and that should fit fairly well there. So logging both things will give you a straight line there. Now you can work out whether they have an optimal age for mating, so you can essentially work out whether you can, in other words, whether as we have the model over here, all it tells us is that as the age increases, the number of successful matings increases. That can't be true because you can't have an increase forever. So one way of adjusting that or checking for that is to use a square term, because the idea is at the moment it looks like that, but maybe actually it can do that kind of stuff. A square term may moderate that in some way. So if you use a square term here in the model, do you get actually a term in this, is the square term going to be significant or not? So we know how this works. We use this I age squared to actually compute the age squared and put the thing in the model instead of just computing it straight away. And so here you can see what happens is, as far as age squared is concerned, it's not significant. It's not significant. So that means I will drop the age squared term in this case. And you can see, of course, also what's happened is by introducing the age squared term, the age term also has become non-significant. So by looking at this here, it looks like the age squared term is not significant. If I keep that model nonetheless, it does have a negative term here, which means that eventually at some age, the successful number of matings by the elephants will start decreasing. So all this doing is actually checking the p-value. You can see I'm checking between the two models here with an ANOVA. So it's ANOVA with the two model objects, GLM1, GLM2 here. And so the p-value here is large, which means the two models aren't different. So we'll pick the simpler model. The simpler model is the one where the second beta is equal to 0. If the p-value here is small, essentially the null hypothesis is that beta 1 is 0, it's not equal to 0. Beta 2, I mean here. So beta 2 is 0, it's not 0. So if the p-value is small, that means beta 2 isn't 0. You'll pick the model with the constraint that beta 1 isn't equal to 0. All right, so model adequacy here at last. How do we check for model accuracy? So the Poisson actually assumes the mean and variance are equal, and you can actually informally check this with plots to see if the mean and the variance change the same way. As the mean goes up, there's a variance. In our plot we saw here, as the mean goes up, have a look at the plot here with the data, which we had a few slides ago. Does the variance increase with mean? Well, pretty clear the mean here is quite small, and so is the variance quite small. But here there's quite spread out as you go to the other part of the curve of the data for higher age. So as the mean increases here, it looks like also the variance increases. But that's an informal check. We should be able to do better than that. Now, as it says here, we can check by looking at the Poisson residuals, the deviances, whether we've got any misspecifications or outliers here. And there are some other goodness of fit tests we can do, which we mightn't bother here. But here is just so what we've got here is we've taken the from the data itself the mean away. So we've actually, if you like, zero, we've got a standard, well, mean shifted, mean zero process here. We've taken the mean away, so instead of going up, it actually goes flat. But you can see the same idea here. As the variance, as the mean increases here, you find the variance also increases. So this is fitted values against residuals. For the normal distribution, we expect actually to have a band, a flat band across with no change in variance or spread. You can see here the spread does change as the mean or the fitted values increases, which means that the Poisson distribution assumption does seem to hold. As it says here, do the points fan out as the fitted values increases? And they do. They're quite well easily observed as fanning out here. There's still this problem with the outlier here, and that may cause us problems. The usual idea again of the Poisson residuals is going to be the observed minus fitted, always observed minus fitted, over the variance. And of course, we've got no choice here but to actually estimate the variance by this lambda hat square root of, because lambda squared is the variance. So from each data point, I can actually take a look at the Poisson residuals, and we can take a look at the plots of those. So here is the Poisson residuals calculated here, and you can see here that the behavior is fairly good, because I've standardized this now. You do expect to see a reasonably flat band. It does seem to work that way. There's not as much change here, and the spread or the fanning out has decreased quite a bit compared to the previous plot that we saw here. So it's roughly constant in this case. Here's a brief recap of things and how they worked for us this week. And here's the last part of the inference stuff here. There are a couple of problems to look at here. So one of the things is this. Let's start here. What if mean and variance aren't the same? For example, if mean is less than variance, or the other way around actually, variance is less than mean. Or variance is bigger than mean. So these are the problems we saw, this parameter that you find in the models coming out in the bottom called dispersion parameter taken as 1. That essentially assumes the mean and variance are the same here. So this is what we call under-dispersed model. Dispersion, of course, refers to the spread. And this is over-dispersed. So this is the first part question, and the second part of the same question is, how do we know? If the mean and the variance aren't equal. And the second question is, often you see in Poisson distributions a lot of zeros. Because looking at counting phenomena, sometimes they just don't happen. So you might have something that looks like this, essentially. You look at the histogram, there's a huge bar here at 0, and then everything is sort of about okay. So here we have too many zeros. So what do we do here as well? If there are too many zeros in the data, then it does not quite fit a Poisson distribution. You can't knock the zeros off, because if you do, then you've lost the Poisson part anyway, because it needs to have a 0 there as well. So what happens in this case? We've got either that the mean and variance aren't equal, one's bigger than the other, and how do you test for that? And what do you do if you've got this case of these zeros dominate the model in this case? Because then what will happen is the mean either gets pulled down, or you get all sorts of other issues as well here. Any questions so far before we continue? So this week's labs in the Poisson distribution. What we've done so far with the modeling is two things only, essentially: the binary logistic regression and the Poisson. So what happens from here on, we'll be looking to see what happens if some of the assumptions, like what we've seen here, don't actually hold. And then from there, we'll move on to the last part of the course, which deals with the likelihood estimations, and we'll see how we go in the last few weeks of that. So before we proceed, two things to remind you of. We have 2 more tests, and they're going to be next week and the week after. So this is week 8, week 9 and 10, the 2 tests, so that they're over well before the end of the semester, which gives you time to work on the exam. The exam format, as I said to you earlier, I haven't decided yet, but most likely it will be a similar format to the tests that we have had, the last test and the next 2 tests, but it will be a bit more substantial. So it's not going to be a one-page report anymore. It's going to be more like a journal article. Now, for those of you who are clever, in the last test, I gave you a reference paper. The data was from that paper that's already been published. Now, many students email me about this, that, or the other, whereas all the information was in the paper. Now, there's 2 or 3 reasons to read the paper. The first is all the description of the data is in there. The second is you can see what we wrote, how we explained things, what we said about model interpretation in the end as well, and maybe there were some hints and discussion of the weaknesses of the model. All that's already there. You're analyzing the same data with a little bit of addition. The data in the paper didn't have demographics like age, sex, all the rest of it. Our data did have that added on, so ours was a bit more richer data in that sense. But overall, it's the same thing. So you should, I hope you did, you should have read the paper, not a very long paper, and well within your understanding as far as the material goes. So that you should have read the paper and learned from that as to at least how to write these kinds of things. The second, so those couple of things you should have picked up from there. Now the next data set you'll get may be similar. It might also be along the lines of something that's been published or is probably going to be published soon enough. And you might have a reference somewhere. If you have it available, you must look at the references. It certainly is very important to be able to read these things now and make sense of them. Yeah, you know, in second year, you know, in science degrees, second year is the hardest year. Easily enough. When you get to third year, by the time you get to third year and understood most of the mechanics of the thing, now everything begins to make more sense. So you must read those kinds of papers that are within your grasp, within your capability, understand them, and learn from them at least how to write stuff properly. So the next test, as I say, when I build up, you will find, I hope it will be similar. But before we disperse today, first of all, 2 things. First thing is, any questions so far? I hope we'll work through the labs thoroughly, yes. Taker. Yes. Well, the idea was that at the moment the regression line is straight line, yeah. So as far as the log model is concerned, log of the mean is straight line, which means as the age goes up, the mean or the log of the mean keeps going up. Now, if you actually add a square term, the thing with a square term is a quadratic looks like this, or the other way around, yeah. Now the hope is you're expecting that if I put a square term in there, then it'll be a negative coefficient, so it'll look like this. In other words, eventually, while the mean with a straight line keeps going up all the time, in logarithmic fashion, with a square it tends to dip down. So we can actually work out where the maximum is. What is the optimum age at which elephants have the most successful number of successful matings? That's why the square term went in there. Now the other thing you can try is, and this seems a bit strange maybe because I've got a log mean anyway, I would try and put a log of the age in the model to test for that. Yeah, because the thing with log age is that at least at the moment, I say, if I look at the age here and take a look at log of the mean, it looks like that. Negative somewhere there actually, it's negative there somewhere, but looks like that. Whereas if I put a log term in there instead of in terms of age, if I put log term in there, then the log flattens off, yeah? So it's going to look more like this. It flattens off, which is a better model than better than the straight line model. So you wouldn't expect the number of meetings to keep increasing, but maybe flattening off. Yeah, that would be a better model. Try that in the lab maybe sometime. I haven't tried this with this data because I'm not going to mess too much with something that's for the moment quite simple, but you can see these ideas we've seen before in other contexts, in the context of normal regression models, for example, where things don't make sense if they just keep going up. You can try a log model where it flattens off or something else similar. So I might try log age instead of just age in the model, and so you'd have a regression that will look something like beta naught plus beta 1 log age. So that will be your log of lambda. But the only other thing, of course, is with log age now, the model interpretation will change. So if I take a look at, using a log model, if I take a look at lambda now, it becomes e to the beta naught times e to the beta 1 times log age, which essentially becomes e to the log age, I'll forget the first term, to the beta 1, and so e to the log age is essentially age. So it's actually a power of age. So it becomes a bit more power function here, and you expect that the coefficient here will be a bit less, so it will tail off as you go through. So those are things that are worth investigating. Any more questions? And the variance for the Poisson is equal to the mean. How is another question altogether? Yeah? Yeah, you're confusing yourself with the normal mean. Yeah? For the Poisson, the mean and variance is equal. So if you look at how probability theory works, you know, if you've done probability theory, that for any variable that's discrete, the mean is going to be equal to the values of x times the probabilities of those values added up, yeah? General. For binomial, if you do the calculations for this, you get the NP idea, and the same with the variance. The variance actually depends on e of x squared. That's going to be e of x squared minus the mean squared. And e of x squared works out in the same way with an x squared there, times the probabilities. For the Poisson, when you do the calculations for this, it will not be actually n here because there's no limit to this, it will be infinity. If you do the calculations, you'll find this works out to be lambda. This also works out to be lambda. No, squared. So not, sorry, it's not squared, lambda. Yeah? The calculations give you exactly lambda there. So that's not a problem, that's just the calculations we get from the theory. Seems that's the case for the Poisson. You're right in one sense because you think the units should be squared instead of just lambda, right? But you see the squares come out from the calculation itself. Yes, another question here. I haven't got to the answers yet. And I haven't got to the answers for this one either yet. What happens if you have a under dispersion over dispersion? So dispersion stuff we'll look at later on a little bit in the course. In fact, next week we'll start looking at those. But we've got data that's dominated by zeros. There's a real problem there. And we'll look at some of those, touch on some of those later on. The modeling aspect in many situations is fine. If the data behaves itself perfectly, modeling is easy. But data sometimes doesn't behave itself. Any more questions? So here's a question I have for you. I'm going to conduct a medical trial. And my context is I'm looking at children. Who will undergo surgery for tonsillitis. So one of the issues with surgery, of course, is, especially with young children, is when they come out of surgery, they vomit. Not a very nice thing to have, and also pain as well. So I'm trying to look at treatments for vomiting. I'm not going to look at the pain for the moment. Now, because they've come out of surgery, you can't give them much to eat. Because it's so raw inside there, to start off with. And they mightn't feel like eating much in the first hour or so. So here is what we're going to do. We'll try something new. The idea is the actual act of chewing stimulates something in the jaw area and all the rest of it, and also the stomach, that may reduce vomiting. So what we'll do is we'll give them something to chew, something that actually is a bit chewy. And what we'll give them is a snake. So it's this jelly confectionery, which is actually quite rubbery and chewy. Actually, that will stimulate all those glands in there, and the idea is it may stop vomiting. So, you are the person in charge of the stats. Because you're a data scientist, right? And we hire you for the job. Interestingly enough, I'm looking for one at the moment, but anyway. So the first question they're going to ask you is this. Before you can run those trials, the first thing you have to do is, what do you reckon? Any ideas? What's the first thing you have to do before you run the trials? Long before that. Sorry? Yeah, before that. All those are correct before that. Yeah, even before that. Okay. While you're doing that, something happens. Somebody else. Yeah. Could, yeah. But even for that, you need something else. Hypothesis. Something a bit simpler than that, something more basic than that, something a bit simpler and more basic than that. If I'm going to go up north in Western Australia and I'm going to study an indigenous population, what do I need to be able to do that? Permission. Who do I apply to? The government. Government, right? So if I have all your student data, yeah, all the student data is available to me, I can see it all. What if I actually, my kids went to university here, by the way, both of them. They're in my classes as well. What are the issues with my children being in my class? You tend to manage to avoid that one, I see. But what's the issue with that? It's a big word that starts with E. T. Ethics. Ethics. So if my children are in my class, I can't mark the exam papers, can I? It'd be unethical. Somebody else needs to do that for me. Likewise here, before I can look at these trials and say I'm going to do this, I need ethics approval. Somebody has to look at the thing and say, all right, you can do that, because you aren't harming anybody. And you have to be careful with these things, as you were saying earlier. Some of the things I have to be careful with. I've got to make sure the data I collect is confidential. Nobody else can see it except the people involved in the trials. Even there, a bit more needs to be done to make sure the trials run well, right? So, for example, me being a statistician, I will not have the IDs of the children. I won't know who they are, any of the details. All I require is the data that I need. So I'll have an ID number of some kind that is on some record somewhere else. So if something happens, I say, look, this child over here, something funny is happening here. Tell me about this. They can go back and check what happened with the child. Something maybe weird or something special with the child. So that is the first thing, to apply for ethics approval. What are some of the things the ethics committee will want to know? You've said some of those before. One thing, tell me that they will want to know. Sorry? Methodology. They want the trial methodology. How will you run the trial? One of the things is that you must make sure that, well, of course, when we take a look at giving the children snakes or otherwise, then of course I need to have a design where I have a control, right? So one group gets the snake, the other one gets nothing, or something similar. So is it the snake or the chewing is the idea here? So it's not the snake, it's the chewing, right? So it's not the sugar. I might give them a lump of sugar instead of something, like the usual stuff. You give them a drug or placebo. So that idea here, I have the control as well. But I'm going to make sure that I have the selection of who goes in the which group at random, randomize that, right? No problems with that. I can do that. That's the first thing. How the trial will run is a separate problem altogether. That's for the clinical trials people to work out, and we can do that, no problems at all. So we'll make sure that's all done properly. So data needs to be stored accurately and properly. It needs to be shared only with those who need to have the information and be confidential otherwise. It needs to be stored securely so nobody can go and have a look at that. And certainly the other thing is it needs to be stored for a certain number of years in case somebody comes back and says, look, my child went through that here and this happened to him or her afterwards. Look at that and tell me what you did to the guy or child or something else. So yes, that needs to be stored confidentially. That's all the part of it. What are the things that the ethics approvers want is very clear here. Is one of the things they'll always want is, make a guess, what will they want in your ethics approval besides how the clinical trial will run, how the data is stored, all those kinds of things, how will you disseminate information. So they want to know, I'm going to publish the results somewhere, but of course when you publish results, you can't publish the IDs of the people, of course you won't do that. What is one thing they will always ask for in these trials? Consent, yep, consent of parents in this case. I have to have that, yep, okay. Well, that's going to be this vomiting and non-vomiting, yes, okay, sure. Some measurable benefit available, yes. They'll certainly look at the stats design methodology, how you analyze the data, what are the stats questions we're asking, hypotheses, those kinds of things have to be a part of those ethics approvals. But there's one particular thing they always ask for. Privacy is part of it, yes. Very important thing. One of the most common questions we get asked as statisticians, the one of them is p-value. You wouldn't think that's so important, but yes, p-value. People want p-values. And the other thing is, starts with this. 2 words, SS. Sample size. How many children will you need? How many? And so that, of course, is a question that you can't ask so straight away because the sample size depends on at least an estimate of variance of the data. You don't have the data yet, do you? So how do you calculate the variance for that? Well, you can still estimate things and work out what kind of difference. For example, if you're looking at this and saying, all right, I want to reduce vomiting over here. So the kind of models you'll be using here will determine for you or work out for you the sample size. You can do those kinds of things. This is the initial stuff, even before you go to the data, right? So in this case, if it's a clever and a good group, they will hire the statistician beforehand, and they'll ask him or her to do the work with them with ethics approval, sample size, how will you manage the data, what kind of data do you want, how do you store the data, what data do you want in the first place, as I said, and what kind of models and stats analysis will you do. All those kinds of the things will be part of the ethics approval to start off with. Once they've cleared that, then the trial starts, or you can apply for funding as well. But funding actually usually requires the ethics approval to be done first, either through your own institution like here, or through the funding body itself. All that's done, now you start the trial, yeah? What data do you need? Okay, you call that, the word for that? Demographics. So the age is one thing, what next? Sex, next? Height, weight, BMI, those kinds of things, right? Might make a difference here. Anything else? any other comorbidities, right? Because you will actually exclude those people. And that's part of ethics approval. Any child with some other complications will be excluded from the trials. So you have usually these procedures of tonsillectomy happen all the time in the hospital over here, and so they'll make sure that they'll pick the children at random, but there will be exclusion criteria as well as to who gets excluded from the trials. Yeah, done. So you've got height, you've got usual demographics like age, sex, height, weight, BMI, can calculate from there. Anything else? Ethnic group, very important. Anything else? Some measure of child's overall health you might want as well, some index of health you might look at. Other things that you will also want is things like the previous history of the child's vomiting, for example. Other things that you might not think important, like does the child have asthma, for example? Are there breathing issues? Does the family have asthma? Motion sickness, those kinds of things all relate to vomiting. So all that variables has to be collected. You cannot collect enough. If you have a few extra variables that aren't important, your model will tell you. Yeah, they aren't significant. But you can't presuppose. We've just, one of our PhD students, one of mine, has just finished her thesis, and the examiner's reports came back here, and the examiner was saying that you've actually got some variables in your model that don't make biological sense. Why do you have them in the first place? And our response is, well, you can't presuppose that. Because often, of course, things that don't make sense to you don't do so because of your current knowledge. And the data and the stats will show you something else that may initiate investigation into why is this the case. You might then discover the biological reasons. Yeah? So you let the data tell the story, not yourself. You don't presuppose this one will be there, this one will be there. Let the data tell the story, and you can work out from there. Sometimes, of course, you get spurious correlation. So it's well known that things like if you look at a person and you look at the income, and you look at things like the education and everything else, and you look at eye color, for example, suddenly eye color becomes significant. Well, that's spurious. Happens sometimes, right? Just relationships that are spurious because of the way the data is. But that's other than that, no. You might do the same analysis again for some other group of people. You find that color, eye color is not important anymore. So these kinds of things we look at. Other than that, of course, you let the data itself tell you the story. So collect what you think is important and what's known from the literature to be important regarding vomiting. Okay, the trials are done. You have the data available to you. And so the data here will be along the lines of the child was given a snake at whatever time after the surgery, and you'll see how much of the snake the child has consumed in an hour. Yeah? So you can measure 50 minutes, 30, 45 minutes, an hour, how much of this 30-meter snake has the child consumed in the hour or so, right? And also you'll be measuring and counting the number of episodes of vomiting that the child underwent through at 0 hours, 2 hours, 4 hours, 6 hours. Count those things, right? What kind of model are you going to use here? What's the STAT model? Any ideas? Poisson sounds reasonable, does it? Because it's a count. It's not binomial because I'm not looking at the situation whether it's a 1-0, does the child vomit or not, although that can be binomial. If I look at, say, just vomit or not in after 0 hours, 2 hours, 4, 8, 2, 4, 6, just if the child vomited or not. That's binary, right? It can be binary. If I count overall the number of times the child vomited in the 6 hours, that's now Poisson. Because here there's no fixed number of trials. In the first instance, binomial is success or failure. Did the child vomit or not? That's 1-0, right? But if I count the number of times the child vomited, that's Poisson. So that's the kind of model I'll be fitting with this data, right? Poisson model. So some of the issues with the Poisson model, as we saw, was, well, if you have two variables that are actually completely aligned with the data in some way, sometimes that happens to be the case, then you will have the situation where the model will tell you that your probability is actually a 1 or 0 in this case. Data completely aligns with something else. That variable has to go, right? Because there's something else happening in the data that completely aligns. Sometimes that happens. Other things that happen is you've got two variables that have the same information. exactly the same, they align exactly with each other. In that case, one variable will be fitted, and the other you'll get NAs in the model fit. Yeah. The third is where some variable misbehaves, and you'll have, in that case, a variable which has a very large standard error. Now, you may have actually many variables with large standard errors, and so you might find, because what people look at is p-values, fantastic, they're all small, significant, bang, rubbish. Look at the other things as well. If you've got large standard errors and large estimates of the parameters, it's rubbish. It doesn't work. And it may be just one variable that's messing everything up. So you must take off variables one at a time until you get to the variable that's causing the problem. Take it out, yeah, and then fit the model again to see whether it behaves. But the variable will be taken out, look at the thing and see what's causing the problem. Why is it a problem? You need to investigate that, right? So having done all this stuff, if the model fits fine, you've got a good model there. Then you get to the other problems of under-dispersion, over-dispersion. What happens if the variance is too large or too small compared to what you expect for the Poisson? Now, there are tests which I hope I'll be able to do some of those next week, where you can actually test, having fitted the model, to see if the Poisson mean and variance are the same. It'll do a test for you. It'll estimate the ratio of those. It'll give you a p-value as well. Right? So it's the ratio of the variance to the mean. It should be close to 1. If it's too small, it's under-dispersed. If it's too large, it's over-dispersed. It'll give you a p-value to say whether it's okay or not. If it's not okay, then you need to modify the model. And that's something we'll discuss next week. The other thing is that, as I was saying earlier here, if there are too many zeros in the data, you know, what we call zero-inflated Poisson model, yeah? Zero-inflated Poisson model. What do you do with that? Well, there are ways to handle that as well. You can actually search those things in the literature if you like. You can do a Google search on zero-inflated Poisson models. You'll find how to handle those kind of things. So in that case, what you would actually be doing is, if you look at what's out there in R, there's a package that does it. So for the zero-inflated case, Poisson, you'll find papers on this, of course, online. This is a common situation. What we normally do is, you've got a large number of zeros over here somewhere, and the rest of the thing is actually not very different from Poisson. So what we do is we fit a point mass there. In other words, we actually put a binomial distribution on top of that. A binomial which estimates the probability of zeros, as well as the Poisson part. Essentially becomes a mixture model of some kind, right? But luckily R does it for us, and you'll find all the things online for R. This is not something I'll pursue here in this class. Of course, it's rather advanced, but I want you to be aware of this one here, because this is a very common problem. So look at the data. If the whole pile of zeros here, and then it behaves normally otherwise, you actually need to consider this zero-inflated Poisson kind of model. Now, my point here is that this is not part of the course as such. But when you go out in the real world, they won't tell you what model to use. You have to work that out for yourself. In fact, you will be telling them, this is how you earn the data, and this is the kind of model we'll be using for this. Because as a statistician or data scientist, part of your role will be actually from the beginning of the trial to actually write with the medical people the ethics approvals. And I can tell you what, ethics approvals for medical trials ain't easy. They want to make sure you have got a calculation of a sample size that's justified, where you can use 100 children. They will not let you use 200, because you can get 200, they won't let you use 200. Use as few as possible to get the result that you want, yeah, to show significance of the result, and proceed from there. Not 200. You just can't pick who you like and use as large a sample size as you want, because of course in stats, the larger the better, right? But no, you can't do that. The other thing with medical trials is, what are some of the other issues with medical trials that you would expect? So you've got surgeries booked in for your tonsillectomy, like over here, and you select some of the people for the trials, and there's enough problems. They sign everything, What are some of the problems you can expect here? Maybe, yes, they'll exclude the person, yes, some exclusions, and we saw some exclusions because of other conditions, but sometimes there are problems in the trial itself, and the person has to be excluded. The child may get sick or something else, some of the complication arises, you've lost the child from the trial. Yeah, well, that's one problem. Other problems? Not necessarily this trial here, but other trials in particular. What can go wrong with medical trials as far as your sample size is concerned? Too many get excluded, you get small sample size, agreed. That's one problem. Any other problem? Big withdrawal, don't turn up. So is book today, don't turn up. Or go somewhere else. Or lockdown, bang, all gone. That's actually happened with us. Everything was delayed. Yeah? Sorry? I'm trying to get it. A death. Yeah, that will be more serious than the medical trial in that case, yes. But that's another case where you've lost the sample size. So in other words, my point is, if you calculate a sample size of, say, 200, you've got to allow the fact you might lose some from the trial for many reasons. One is they might withdraw, they mightn't turn up, or they might be excluded later on for other reasons. So you've got to balance that by saying, all right, I'm going to allow for this by inflating my sample size by 15% or 20% or whatever. Yeah? And that is allowed by ethics approvals. The other thing is in things where you have to make measurements over some person over time, of course, there could be lack of follow-up. So some of the work I did with this guy in Subiaco who's a knee surgeon is he's looking at his patients over 2 years to see how they're proceeding. They don't turn up. They're gone. You've lost them, right? So you've got something like a surgery has been done to them, it looks okay in the first 3 months or so, then they don't turn up at all. You've lost the person because of that. So again, your sample size goes down from the trial. So yes, as I was saying earlier, this isn't part of the whole course, but the thing is, this is the kind of stuff you'll be doing out there as a data analyst, data scientist, statistician. It's real stuff. This snakes thing has just been completed in the Perth Children's Hospital. Yeah, real trials we worked with. At the moment, I'm just doing the data. And guess what? That's your next test. Real data. Yeah? Textbook data is fantastic. Textbook data works perfectly. Real data doesn't work so well. Now, luckily for you guys, as with the first data set you did with just one was easy in many ways, simple data. This is a bit more complex. You actually do have the problem here of zero-inflated Poisson process. Yeah? So I can adjust the data to make sure it behaves well enough so you can do a modeling exercise and get something out of it, but you might still find a few problems here and there you might have to discuss somewhere. Yeah? But as I say, this is the kind of stuff you will be doing in real life. Medical stats at the moment is booming, man. You know, I've got so much work with the Perth Children's Hospital, I'm looking for another person to help me. I can't find one. Can't find one. That's how bad it is. So this is a large booming area. But the thing is, in my opinion, and I can say it loudly, or not that people are listening, is that I don't think what you're doing in data stats as a master's prepares you for that. It doesn't prepare you for anywhere near the kind of stuff you'll be out there. Your knowledge in stats is rather patchy from what you do over here. Very patchy indeed. But you can fill it in yourself, right? You can fill it in yourself by your side reading. In other words, you may get sort of some of the core bits and pieces. There's a lot more to it out there. That you can catch up on by yourself. So my advice is do the thing now. Don't wait till the job hits you and suddenly you have to work the thing and work it out as you go. Do it now. Learn as much as you can. Yeah? And it'll really serve you well. The thing is, when you go out and work in the careers, you know, nobody tells you this kind of stuff. I had to learn this thing myself, hard for experience and all the rest of it. When you go out in a career, whatever you work at, you don't want to be stuck at the bottom, do you? I have somebody I know from some other liaison somewhere else who's come into a job and he's been in a job for the last 35 years. Others have come in and he's taught them the job and they've gone up and become his bosses and he's still there. You got to work out in every career. What are the key things that the career requires? What do you need? What are the focus? What's the main key elements that will allow you to go up? and you focus on those things. Focus on those things. Everything else is peripheral, right? That's the main thing. You progress in your career, you've got this idea of I'm going to make it here and here and here. Then focus on what does this job require for me to shine, so I'm noticed. Yeah. You don't have to go and tell everybody what a great guy I am, how fantastic I am, I can do all this stuff for you. Yeah. No, do it and shine, and you'll be noticed. Yeah. You'll be noticed. That's what you're going to do. Instead of blowing your own trumpet, let your work shine. Because managers and people in many of these places aren't idiots. They can see through a whole just person who is, as they say in the language, gas bagging, right? They can see through a whole lot of hot air. They can see through it, and they can pick the people very easily. So make your work shine, and you'll find you will shine as well. You will go up. Now, okay, so there are places where there's favoritism and all the rest of it. Despite that, if you are capable and you do the work and you make yourself shine, you can't but go up. You'll find that's the case. Yeah. So when you're out there in a year or 2 years' time or whatever else, and you find your first job, find out the things. What are the key aspects of the job? What is the primary thing you have to do? For example, universities, the primary thing is not teaching, it's research. It's not teaching, it's research. Nobody cares, and I can say this loudly enough, maybe they're hearing me out there, and maybe they'll come and talk to me afterwards. Nobody cares about teaching, because you can do what you like with teaching. If your research is stellar, you'll go up. Yeah? We have people in the place who couldn't teach to save their lives, and they become professors. Nothing personal, that's fine, but research counts. Nothing else does. Yeah? So that's what you have to focus on. So when you go on your first job somewhere else, pick out the key elements. Speak to people by all means. Ask them, especially those who are a little bit higher, or maybe some, people have gone through that path a little earlier. Ask them, and not sort of bluntly, but ask them, what do you do? How have you done it? How did you get here? Those kind of questions, the kinds of key questions. And the other thing is, it's very important in these job situations, and it's something that most people actually have problems with this. Don't talk too much. Listen more. Because by listening, you will learn so much more than by just talking all the time. And if you do talk, make sure you ask questions, and the right kinds of questions. Having said that, any questions? All right, we'll see you next week. Thank you.